For centuries, scientists believed heat was a fine, invisible fluid called caloric. The theory suggested this fluid filled the pores of a substance, flowing from hot bodies to cold ones until their temperatures eventually equalized. That concept was upended in 1798. Benjamin Thompson observed that the boring of a brass cannon generated immense heat, enough to boil water. He noted the heat produced depended entirely on the work done by the horses turning the drill, and it didn't matter if the drill was sharp or dull. If heat were a fluid stored in the pores, a sharper drill would have scooped more of it out. Instead, Thomson's observations proved that heat is a form of energy, specifically the energy of the disordered, random motion of molecules. This distinction separates mechanics from thermodynamics. Mechanics focuses on the motion of bodies under forces, like the trajectory of a bullet. Thermodynamics, however, is concerned only with the internal state of that body. This diagram represents a gas chamber defined by its macroscopic variables. Because we cannot track trillions of individual molecules, we specify the state of a system using measurable properties like pressure, volume, and temperature. When these variables remain constant over time, undisturbed by the surroundings, we say the system has reached a state of thermodynamic equilibrium. Consider two separate gases, System A and System B, initially possessing entirely different pressures and volumes. We separate them with an adiabatic wall, a perfect insulator in thermodynamics that prevents any flow of heat energy between the systems. This absolute boundary prevents energy transfer. System A and System B maintain their distinct pressures and volumes indefinitely, completely unable to affect one another. Each system exists in its own independent equilibrium. The variables on one side are frozen, completely isolated from the variables on the other. Under these constraints, the two systems have zero interaction, effectively existing as two separate physical realities despite their proximity. To understand how thermal equilibrium is achieved, we must change the nature of the boundary. We replace the insulator with a diathermic wall, a conducting barrier that allows heat to flow freely from one system to the other. The digital readouts for pressure and volume begin to fluctuate as energy spontaneously transfers from the hotter side to the colder side. The systems are no longer isolated. They are actively negotiating a new shared state, searching for a point where the exchange of energy finally balances out. This energy in transit is what we call heat. It is the mechanism that alters the internal energy of each system as they move away from their initial states. A diathermic wall forces these two separate gases to reach a compromise, continuing the exchange until they settle into a unified state of rest. Eventually, the fluctuations stop. The macroscopic intervals lock into place, and the flow of heat vanishes. At this precise moment, we can say that System A is in thermal equilibrium with System B. This observation is the foundation of the zeroth law of thermodynamics. If two systems are separately in thermal equilibrium with a third system, they must be in equilibrium with each other. This law suggests that there is a specific physical quantity that must have the same value for both systems. We call this variable temperature. While the pressure and volume might differ based on the size of the containers, the shared temperature is the universal marker that confirms equilibrium has been reached. This isn't just a theoretical concept. In a steam engine, we harness the heat of the steam to do useful work by moving the heavy pistons that rotate the wheels of a train. We are effectively controlling the drive toward equilibrium. Thermal equilibrium provides the physical basis for our entire concept of temperature. It is the condition that allows us to measure, track, and ultimately master the flow of energy in the modern world.